welcome to Year 1, Chapter 1 for Mechanics. This one is looking at the basics, which do some modelling and a couple of fairly straightforward skills. First with the modelling, in mechanics you have a lot of things to basically define. So the odds are for most questions you see, you start with like a 1-mark question saying define a rod, define a uniform body, etc. So we're going to go through what all these mean, but you should know them all at least enough to write down a decent definition. So most things you do work on, you're going to treat as particles. That basically means they're infinitely small, so we can ignore rotational effects and air resistance. Next you've got a rod. This is basically like a really thin plank, often used in kind of like seesaw questions. You'd assume for the rod it's typically light unless told otherwise, so it might have no weight. It'll be infinitely strong, so it cannot bend or flex. And those are the two key things. And it's basically treated as one-dimensional, so it'll have no width or depth. Moving on from that, we have a lamina. That's basically, you can think of like an infinitely thin piece of paper. So it's got length and width, but no depth. And again, you'd also assume it can't bend unless told otherwise. Uniform bodies, if we go back to our lamina, if it's uniform, that means the weight is equally distributed throughout the entire lamina. Or in other words, it's equally dense. So therefore its centre of mass will be right at the middle. A light object has no mass. Again, it can be particles, rods, laminas if you're told. Most things you're told explicitly if they are light or if they are not. Inextensible strings, so often you might have some sort of pulley question. That just means the string cannot stretch or contract, so no sort of force is lost to the string. Other ones you see is like a car pulling a caravan. If this is inextensible, it means all the force from the car will go straight to the caravan. None will be lost in stretching that string. If you have a smooth surface, that means there is no friction. If you have a rough surface, that means there will be friction. If you've got a wire, that's basically like a rod, but made out of metal. Already says it's a one-dimensional piece of metal. A smooth and light pulley, all pulleys you see will be smooth and light. Basically all it means is all the energy will transfer straight through the pulley, just like with our inextensible string. A bead, that's when you basically have a particle on a wire. So it's a particle with basically a hole in it. You can thread a wire or string through it. Peg, that'll be something you can attach something else to. So you might have a peg with a pulley on it. Air resistance, the force in the air, typically slows things down. In most cases you will ignore it. And lastly there is gravity. Okay, gravity you see in diagrams with 2 arrows for acceleration. And in this we treat it as 9.8 meters per second squared. So those are definitions. You're not supposed to know all of those. Next we have SI units, which stands for something in French. That's basically for every formula we use, they only work if we use these units of measurement. So for example, if you had length in centimeters, before you could use any of the formulas we're about to show in other videos, you would have to first convert it to meters, same with time, etc, etc. I'll quickly go through that. So all these in SI units. So 2 kilometers, we should know that 1 kilometer is 1,000 meters. So we would just do 2 times 1,000, which gives us 2,000 meters. Next we've got 2 kilometers cubed. You do roughly the same thing, however because it's kilometers cubed, you'd have to times it by 1,000 3 times. So you times by 1,000 cubed. That will give you 2 billion, which I won't write down. Slightly more awkward is when we've got stuff like 3 meters per minute. So again, we want all speed or anything like this to be meters per second. So we need to go from minutes to seconds. You would normally times by 60, because 1 minute is 60 seconds. However, when it's when you're basically dividing by that unit, we need to divide by the number instead. So you would then do 3 divided by 60, which gives you 0.05. And again, 3 meters per minute squared, because it's per, we have to divide. So you'd do 3 divided by 60 squared. Okay, so just do 2 more. So these are both densities. We want densities to be kilograms per meters cubed. So the only problem is the grams. To go from grams to kilograms, we times by 0.001. So you would do 210 times by 0.001, which gives you 0.21 kilograms per meter cubed. Here we've got both these in the wrong units. So first we need to sort grams out. We just did that. So we would do 43 times 0.001. Next we've got centimeters cubed. To go from centimeters to meters, you would normally times by 0.01, because 1 centimeter is 0.01 meters. However, because this is because it's got a minus power, we divide instead. So we divide by 0.01. And lastly, it's centimeters cubed, so we need to cube this thing here. Okay, so these rules feel a bit arbitrary. Basic rule of thumb is you always want the same power that you've got here to over here. And if it's anything per minute squared or you've got a minus power, you want to divide rather than times. Then type in your calculator, work it out, and that'll be fine. That'll be the density in kilograms per meters cubed. Okay, the last main chapter skill from this first chapter was using equations to work stuff out. So we've got the height football after it's been hit follows this equation. Part A, we want to work out the 2 times when the ball has a height of 0 meters. So very straightforward. So we use this formula. We're told the height is 0. So we now have this formula to solve. Okay, it's really straightforward to solve. We can times both sides by 10 to get rid of the 1 over 10. Then you may as well just factorise this out. And we have this. This will equal 0 when either bracket equals 0. So either t is 0 or this thing here is 0, which tells me that t is 7 over 2 or 3.5. And both of those will be fine. So that's part A done. Part B, we want to work out the maximum height of the ball. Okay. So, this isn't obvious, but you should know a few basic facts about a parabola, which is basically what this is. If I do a quick sketch, it's going to look something like that. Height of 0 is 0, and height of 0 at 3.5. This is a parabola, which means it's reflective, so therefore its highest point is going to be in the middle. So the middle of 0 and 3.5 is going to be 1.75. That's going to be at its highest, because it's between the two zeros. We're going to work out the height. All you need to do is replace time with 1.75. Okay, and all these questions are doing is making sure you are okay with the basics of how to use a formula. That's all the testing, and this first chapter starts off fairly easily. So that's all for now, and thanks for listening.